Arithmetic Dynamics, Number Theory Meets Dynamical Systems. This is an introduction to the fascinating intersection of two major areas of mathematics. Arithmetic dynamics is the study of number-theoretic properties of orbits under repeated application of polynomial or rational functions. Given a rational function f mapping rational numbers to rational numbers, we study the orbit of a point alpha which consists of alpha, f of alpha, f squared of alpha, f cubed of alpha, and so on. Let's consider the two mathematical worlds that come together in arithmetic dynamics. On the one hand, we have number theory, which studies properties of integers and rational numbers. It is an ancient discipline with deep structural insights. On the other hand, we have dynamical systems, which studies iterative processes and long-term behavior. It is a modern field analyzing temporal evolution. Arithmetic dynamics acts as a bridge connecting classical questions in number theory with dynamic questions. For example, a classical question might be, how many rational solutions does this equation have? A dynamic question might be, what happens when we iterate this function? Arithmetic dynamics has key applications in the following areas. Firstly, Diophantine Equations, where it helps in understanding rational solutions through iterative processes in orbit analysis. Secondly, Cryptography, where it is used in analyzing pseudo-random sequences and discrete logarithm problems. Thirdly, Random Number Theory, where it helps in studying distribution properties of arithmetic sequences. Fourthly, Complex Dynamics, where it bridges p-adic and complex analysis through dynamical methods. Let's define rational maps. A rational map is a function f of x equals p of x divided by q of x, where p of x and q of x are polynomials with coefficients in a number field. Examples include f of x equals x squared plus c, and g of x equals 1 over x. These are simple cases that exhibit complex dynamics over number fields. Given a rational map f and a point alpha, the orbit is the sequence of iterates under f. The orbit sequence is as follows. Alpha goes to f of alpha, goes to f squared of alpha, goes to f cubed of alpha, and so on. The arithmetic properties of these orbits reveal deep connections between dynamics and number theory. We study rational maps with coefficients in number fields, which are finite extensions of the rationals denoted by q. Common examples of number fields include q, q of root 2, q of I, and q of zeta n. Here are some key theorems in arithmetic dynamics. The first is uniform boundedness. Heights of points in periodic orbits are uniformly bounded, such that h of f to the power n of p is less than or equal to c, for some constant c. The second is density results. Pre-periodic points are Zariski dense in certain varieties, such that the absolute value of per subscript n of f intersected with k bar is less than infinity for number fields k. Future directions in arithmetic dynamics include, first, p-adic methods, developing non-Archimedean analogues of classical complex dynamics. Second, higher dimensions, extending results to multivariable rational maps and algebraic varieties. Third, Galois theory, understanding Galois actions on dynamical structures. Fourth, computational tools, developing algorithms for orbit analysis and height computations. The bridge between number theory and dynamics continues to reveal new landscapes. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.